Thank you so much, Egu, for the introduction and the opportunity to interact with members of the Colorado Foothills World Affairs Council, an organization that, if you go to its website, the first thing that comes out is this beautiful view of the Mount Vernon Country Club. And there is a statement of the purpose of this group, which says, the world is a complicated place. Understand it from the Colorado foothills. So when I received the invitation from Hugh, the first thing that I did was to look at about 10 or 12 of the different lectures that you have had in the last year or so. And boy, the world is a complicated place. Conflicts and war and population growth and climate change, all sorts of challenges. So what I decided to do, said, well, if this is what the group likes, we'll keep the theme going. But instead of focusing on how the world is a complicated place, we're going to talk about how outer space is a complicated place and how it's important to understand it from the Colorado foothills. And I'm going to focus on a topic that, space is so vast. I could go into the mysteries of space and all that, but I'm just going to concentrate on a very narrow and a very small topic. And one that is actually one that has actually caught a lot of attention in the last 10 years and a lot of hope of development during the for space circles. But one that is very dear and close to the heart of Colorado. In fact, it's a topic that justifies the existence of the state of Colorado. And that's the topic of resources. Let me explain why resources are so important for Colorado. This is a map of 1823 by Stephen Long of Long's Peak fame when he explored this region of the country. And when he got to this area, to the Colorado foothills, he actually wrote on the map the following. He said, this is the Great American Desert. And he described it as follows. He said, almost wholly unfit for cultivation, and of course, uninhabitable by a people depending upon agriculture for their subsistence. He mentioned that practically there was no wood, no water, lack of communications. It was an inhospitable environment because of American Indian tribes. And so he added that it will be proven an insuperable obstacle in the way of settling the country. That was 1823. 36 years later, gold and silver was discovered in the Colorado foothills during the Pikes Peak Rush, during what was Kansas Territory. Then it became the Colorado Territory, of which Golden was the capital. And finally, it became the Colorado State, which in 2024, if you consider, which it is, a state of Colorado, it is the 8th in the nation on personal income per capita. If you consider Colorado as a country, it is the 30th largest GDP. And related to this talk, Colorado is the second largest aerospace economy in the US. Not bad for a place was an obstacle for the growth of a nation. So just as resources were so important for Colorado, to explore it and to develop its economy, it's important now to talk about how resources beyond Earth will enable both exploration, but also will usher us into the new space economy. And it's important for all of you to understand what are the opportunities and the challenges as we start setting up for doing this type of things as the Colorado Foothills World Affairs Council. And you'll see why the Colorado Foothills are so important to this topic. Now, before we start heading out to space, let's actually look at resources and the importance of them in a planetary body that is very familiar to us. And that is our planet Earth. A planet Earth where natural resources have been the driving force behind exploration, but also the means to do so. And how resources have become an integral part of our lives, our society, and our economy. And to learn from what we have done for thousands of years in this planet and see how we can apply these lessons as we look for resources beyond Earth. So before heading into the future and looking at what's coming up, let's actually go back, way back in time, let's say 120,000 BC, and meet our ancestors, the Homo sapiens, that, because of droughts and environmental degradation and population growth, left their birthplace, their cradle, in the southern part of Africa, and started heading to other parts of the continent, to Europe, to Asia, looking for basic survival. They were looking for water and food. They were not just trying to see what was on the other side of the mountain or these romantic views of exploration. They were thirsty and they were hungry. But what happened in the process, and this is going to be important as you start seeing the similarities between Earth and space, what they did in this process, they developed technologies, how to control fire, how to preserve food, how to develop tools to live in more extreme environments every year. 15,000 BC, when at that time, the energy capture was about 5,000 kilocalories per capita per day. This is pretty much what we need for basic survival. Although nowadays, kilocalories sounds too big, so now we use calories per capita per day to feel a little bit better. So just calories, not kilocalories. Once we crossed to the Americas, 15,000 years ago or so, then it became the time of the first economic revolution. That was agriculture, that allowed humans to finally settle and start wandering around and store food and energy. It was also around 8,000 years ago when mining and metallurgy was invented, and that allowed us to use resources not just for survival. It was used for things. At that time, I just got to say, the energy capture grew about an order of magnitude, 30,000 calories per capita. Then we started using resources for sorts of things, jewelry, also making coins, the first coins that were minted in 650 BC in Turkey. And so this is a time when we start using resources for other means. In the 15th century, we started crossing the oceans. And there was looking for resources that were important for trade. Silk, spices, gold, silver. In the 19th century, it was about searching for oil all over the planet, oil which still is our main source of energy. When that happened, the energy capture per capita went again another order of magnitude. So now we're actually using a lot of energy per person, about 200,000 calories per capita per day. And the search for resources has not stopped. It has gone unabated. In the last 20 to 30 years, it has been about these obscure elements on the periodic table called the rare earth, with very strange names. But they are now the basis of our renewable and communications industry. So as you can see, resources on Earth have allowed us to explore every corner of our planet, have allowed us to live off the land in ever more extreme environments, and they have become the main engine of our technological society. So what happened when we started going to space? Why did we start exploring other places? Well, it's sort of a tale of survival, but not the one that we had from Homo sapiens. This was the main competition between the Soviet Union and the United States that were trying to go for the higher ground and to prove their technological superiority. That's what launched us into space. But once the race was over in the late 1960s, we kept going. And we started gathering scientific knowledge with all sorts of probes. So by now, we know every planet and moons that are out there. But something happened on our way to heaven. We realized, like in any human activity, that space had value, that could be useful to us. And without noticing it, we have become increasingly dependent of our assets in space, to the point that if we were to suspend all of our space assets, it would bring our civilizations to its knees. And this started with a small satellite called Telstar in 1962, the first privately sponsored telecommunications satellite that for the first time gave us real communications between Europe and the United States. Before that, if you wanted to watch a soccer game, you have to wait a couple of days or 3 days. But here you can actually have things real time. And what Telstar did is to utilize the first resource in space. And that is simply location, the view from above. With this, we have global communications. We got weather forecasting. We can pinpoint every location of the planet with extreme accuracy. We can monitor the health of our planet as we continue using many resources here on our planet. And it's not just the first space resource. This is the only commercial use of space. Telecommunication satellites account for about $470 billion a year industry, quite big, that it has been forecasted to go into the trillions in 30 years. Now, you have seen how we have grown more and more used to what's happening in space. But in order to get to the trillions in 30 years, we're going to have to utilize other resources other than location. And there's plenty of elements of interest out there. I mean, there's pretty much a limitless amount of resources in the solar system. But here, there's an important definition to make. A resource has value by its utilization. If not, it's just an element of scientific interest or curiosity. It has to have an application. There's got to be a demand to make an element a resource. And there are 3 steps that one needs to follow if you're going to extract and utilize resources on Earth, Mars, Moon, wherever you go. And these are the following. First, you have to have a recoverable resource. This means you know an element with enough geological, engineering, scientific certainty, but also legal, economic, environmental, that you know that you can go after it. That's what's called in the mining and the oil and gas industry a proven reserve. Other than that, you need a technology to recover it. And third, as important, if not more important, you need a customer. If there's no demand, you can have as much of an element as you want. That is not a resource. So during my presentation, I'm going to go through this step by step. We're going to identify the resources. We're going to look at the technologies that we are right now developing to extract them. And we're going to look at who is interested on space resources. So let's take first a look at recoverable resources. Other than the location and view from above, the moment we cross our atmosphere, you encounter properties that are really hard to replicate on Earth. Low gravity, ultra-high vacuum. It's really hard to do this, but you have it in low Earth orbit. And this is an excellent environment in which to develop products with properties that are very different from Earth. In fact, there are already companies on the space station developing ultra-pure fiber optics, with much higher bandwidth, much purer elements, because they can do it in lower gravity. We have pretty much limitless solar energy that can be used to power spacecraft. But think about what we can do. If we can capture this energy in orbit, in large solar collectors, and beam it down to Earth in microwaves to individual points or rectangles. And we have 24/7 energy without worrying about clouds, without having to plaster the whole planet with solar panels. And this is a way to supply energy to the world in incredible amounts. This was a concept about 30 years, which pretty much was science fiction. It has become more and more real. And in fact, it's now a field called space-based solar power, in which there's more and more countries interested. In fact, China is already testing some prototypes, and there are private companies doing the microwave beaming. In fact, just last month, the first journal on space solar power and wireless transmission came out from China. And so this is going to tell you a lot into who's doing who in things in space, and this is something that you should be very interested in world affairs, on what is happening in space. That is very similar to what is happening on Earth. So these are the intangible resources. These are things that you don't mine. These are things that you collect, but they're becoming very important. If we want to have more concrete elements or to see what's out there, let's start our trips to space. So let's all hop in a spacecraft and let's go to our nearest celestial neighbor. Let's go to our moon. Our moon, that when we got there about 50 years ago, it didn't show any signs of any interesting resources. In fact, if you listen to the recordings from the second man on the moon in Apollo 11, you can hear him coming out of the lunar module and looking around, and he called his surroundings magnificent desolation. There was nothing there, very similar to what Stephen Long said about Colorado. There was no water to drink. There was no wood to do anything with it. There was no communications. It was an inhospitable environment, not because Indian tribes, but because radiation and micrometeorites. There was no oxygen to breathe. And so there was not much hope that there was anything of use. But our view of the moon has changed drastically with the decades after Apollo 11. Because of several orbiters that we have sent around that have given us remote sensing data, and now we know a little bit more about that. We have actually picked up rocks and soil. Apollo brought us 382 kilograms. There were a few grams that were brought remotely by the Soviets, the lunar missions. And just a couple of years ago, China joined the group and brought some samples from the moon, about 2 kilograms. And this material has, and the remote sensing has changed our view of the moon from magnificent desolation to a place that is quite rich in potential resources for the future. So let's take a look now at what are those potential resources. Well, let's first take a look at the two faces of the moon. You have the near side and the far side. Mind you, it's the far side. It's not the dark side of the moon. And that's a common misconception. And it happened because maybe you remember this, but in high school there was this group called Pink Floyd that talked about this dark side of the moon. Great album. Just a misconception of the moon. There were also novels that came out on the dark side of the moon and all that, and that caused confusion. But let me assure you that there's plenty of light both on the near side and the far side. It just so happens that the moon, it's tidally locked to Earth. So what does it mean? That one revolution of the moon coincides with one revolution on the Earth. So you're always looking at the same side. But if the sun is over there, this is the sunny, we call it dark side, but it's plenty of sun. And then it comes over here, it becomes dark. But you're always seeing the same face of the moon. But both sides have plenty of light. But because the near side is the one that we see from Earth, this is where all the action has happened in terms of landings. The United States, the Soviet Union, China, India last year showed up with its landing very close to a very high latitude. Just this year, in January, there was a mission from Japan that arrived to the moon. It had some trouble, it tilted, but survived. And the first privately sponsored mission from a company called Intuitive Machines from the United States landed for the first time in the South Pole. And you're going to be seeing a lot of this action. Actually, starting this year, you have probably 3 or 4 or 5 different landings. And this is where all the action, and a lot of the action is going to take place in the South Pole. And I'm going to let you know why in a moment. So the far side has been forgotten. But just a few years ago, the Chinese landed on the far side. So again, China is really becoming very influential, and they landed on what's called the South Pole Aitken Basin. This was one of the largest impacts on the solar system. An asteroid hit it, broke the crust, and lava came out, and that's why you see it a little bit darker, because this is where some interesting lava flows came out. And they landed on a nice, smooth place called the Von Karman crater. And not only landed, they actually have a rover that gave us the very first views of a place that we have never seen up and close. This is the far side of the moon by the Chinese. And as you will see in a moment, there's a lot of interest on this area, not just for scientific purposes, but also for resources. So you can start seeing what is happening on the moon in terms of competition. Now, let's take a look at some of the resources on the moon. Common to both sides, one of the most abundant resources is oxygen. Now you will say, what? There's no atmosphere, I cannot breathe oxygen. 45% of the moon is oxygen. Where is the oxygen? All the geologists here in the room. It's in the rocks. So the rocks are oxidized. So you just need to heat them up and the oxygen will come out. You have 20% is silicaceous material, which is so important for the semiconductor industry. But that's where the commonalities end. In order to see other type of elements, you have to look at the geology of the moon. The moon was formed very differently from Earth. In Earth, we have tectonic plates, earthquakes, we have wind and all sorts of erosion. On the moon, most of the action happened at the beginning with some bombardment of asteroids, and it formed the geology of the moon, and that explains the resources. So the main geological feature, before not going into many details, you can see some dark spots. Some people see the man on the moon. I see the rabbit on the moon. I don't know what you guys see, but and you have there, that's the Maria. It was named Maria by Kepler because he thought it was seas, Mare. And he was almost right, because these were lava seas at some point. These were places where there was large impacts. Lava came out and filled out those very smooth parts. So there's volcanic material, basaltic. It's about 27% of the moon. The rest, 83%, is this whitish material, the terra. These are the highlands, the primordial crust of the moon that has not changed a bit in billions of years, other than being exposed to a lot of impacts. It's an orthositic material for some of you that know those minerals. And so, interesting enough, nature has helped us to look at where the important resources are, because The near side is mostly where we see things. Let's take a look at some of them. This is the distribution of iron, which is so important for civilization. It's mostly concentrated in red here in the near side. But guess what? There's significant amounts exactly where the Chinese landed on the far side of the moon. Titanium. Oh, sorry. Titanium, that is important for aerospace companies. Also, mostly on the near side. There's a little bit on the other side. The moon has also a very creepy region to it. Creep, but creep with a K. It stands for potassium, rare earth, and phosphorus. This is a place on the moon that stayed liquid while the rest was crystallizing. When it was a magma, it started crystallizing. Instead, it stayed like that because it had radioactive material. In fact, it has uranium and thorium. This is a map of thorium. So you have very important elements that are important to us, radioactive elements, rare earth, potassium, phosphorus on this very unique region. Now, the first thing you do as a mining engineer, you have identified the resources. Fine. What is the first thing that, if there's a mining engineer here, you got the rocks, you know where the elements are. What's the first thing that you need to process in order to extract the material? What is the first thing that you do? Dig it out, drill, blow it up, dynamite, whatever it is, pulverize it so then you can start using it in machines. Luckily, again, nature has done, and actually breaking rock takes about 5% of the total energy consumption in the world. Just 5% it takes to break rock. But luckily, nature has done the work for us on the moon. Now, why is that? Because the moon has been bombarded for billions of years by comets, by asteroids, by meteorites, all sorts of objects that what they have done is by impacting the bedrock of the moon, they have, in the process of doing that, they have completely pulverized the surface of the moon and turned it into a very fine dust. It's so fine, it's about 70 microns, 10 to the minus 6 meters. It's a very small amount. And that's what we call the lunar regolith. And that's why you see the footprints of the astronauts on the moon. You don't see them walking on rock or bedrock. They walk on this very fine dust that has been pulverized after billions and billions of years. And so the material is ready to go. We just pick it up and process it and extract the material. Well, not quite. Things are different on the moon than are on the Earth. If you look at dust on the moon, if you go to a river or a sandy beach, you have very nice, really rounded particles. There's erosion by water and by air. There's no atmosphere on the moon. There's no water erosion. So what you find instead is these very jagged edge particles, very angular, glassy because they've been melted down. They're extremely abrasive. So you have to be careful when we start doing this that it's going to eat up your machine in no time. And if you inhale this, your lungs are going to be gone in no time. So dust is going to be one of the big issues. It's great because it's where the resources are, but we're going to have to be very careful with that. The other thing that has happened on the moon is for billions of years, it has been bombarded by what's called solar wind. These are particles, ions and protons, and because the moon doesn't have a magnetic field, they just get implanted in the soil along with the rest of the lunar dust. This doesn't happen on Earth because in Earth we have a magnetic field that protects us from radiation, so we get to enjoy it in romantic views like this. This couple, not knowing that this is deadly radiation, that means that you enjoy the aurora borealis, but the Earth's magnetic field can actually take care of that. But on the moon, it doesn't. So again, this is going to be quite a challenge because you're going to be exposed to that. But one of the things that the solar wind brings is important elements. It brings, for example, hydrogen, helium, nitrogen, and carbon. This is actually one of the few sources of carbon on the moon. And the moon, we don't have fossil fuels. The only source of carbon actually comes from the solar wind, and it gets implanted on the soil. So along with everything that the moon has, you have these particles that come from the sun. In fact, there's an element that was discovered on the moon during Apollo 17, one of the last missions by a geologist, that became of interest because it's in larger abundance on the moon than is on Earth. It's what's called helium-3. It's an isotope of helium. Just think about a helium atom and you just steal a neutron and that's what you have. And the interest about helium-3 is because if we were to do fusion energy, not fission, fission is just splitting the atom and breaking it up so that there's energy coming out. But if you can fuse 2 elements of helium, really tight in a reactor, and you generate protons, direct electricity instead of going through the steam cycle. And the product is non-radioactive helium. This is what you use in the balloons for your grandkids, and you can inhale it and talk funny. Just don't do that at home. But that's the importance of this. The thing is that fusion energy is still not controlled, and so that's probably something more for the future. But that's some of the interesting things that come from the sun. Everywhere we go, we ask the question, well, how about water? Just like Stephen Long, I'm thirsty, I had to drink, there's got to be some water, where there was not much hope that there was water on the moon at first. And this is because this strange property that the moon has that is only tilted about 1.5 degrees with respect to the sun. The Earth is tilted like 23 degrees, and that's why we have winters and summers, but the moon is not. And so what happens is that during a typical day and night cycle, the whole surface of the moon is illuminated by the sun. There's even this wobbling or precession that the moon has that actually exposes every surface to the sun every 2 weeks. So when it starts wobbling, you can see, for example, how the light reaches also the poles. You can wobble it. So any hope that there's any water on the surface literally evaporates. But some scientists started saying, all right, if that's the case, there's got to be very oblique sun rays on the poles. So if you were standing on the pole, the South Pole, for example, where everybody wants to go, and I'll explain why, you will always see the sun in the horizon. It will be quite a depressing place to be because there's always the sun like it's trying to fade. And so people say, well, some scientists say, well, what happens if you're there? And yeah, you have illumination. But what if there's deep craters that have never seen the light of the sun in billions of years? And this is actually a picture of the moon during a typical day and night cycle. And there you can see in the South Pole that some of the craters, let's pick one of them, for example, right here, that all of them have places where the sun never shines. It shines around it, but here nothing happens. So what if water from comets of asteroids just migrated to these places, which are extremely cold, about minus 130 degrees Celsius, and they may still be there? So in the late 1990s, there were several spacecraft that were sent to investigate this possibility. And started in the 1990s, late 1990s, by Clementine, that had a radar that started bouncing signals and said, well, it looks like there's water. Another mission called Prospectors they use a different technique. It can detect hydrogen, not necessarily water, but there were strong signals from hydrogen. The Indians sent another probe and said, yeah, it looks like there's some water in there. And the Americans had the Lunar Reconnaissance Orbiter that is still going around and saying, yeah, it seems like there's some water. But if you're a mining engineer, you just don't rely on what the sky can tell you. You want to touch that thing. You want to see it. I want to see the water because it may be an indication. I want to see how much is it, what is the concentration. And so that's what happened. Once these were the signals that were collected from all this, they say, well, okay, let's go and have an impact on one of those craters and see what comes up. So they look, where is the strongest signal? Well, it seems like in this crater called Cabeos. So there was a mission in 2009 called El-Cross that did exactly that. It launched one of the satellites, but then at the end, there were 2 spacecraft that separated, and one of those, the white one, was just let go at the highest speed possible to impact Cabeos about 10 kilometers per second. And it hit it so hard that a plume came out. You can see it here. And for the first time, we were able to detect and measure water ice, about 5 to 6% of that plume. So that was very encouraging. Finally, we have a confirmation of what's called ground truth. And not only water, but all sorts of elements that were detected, which is important from the point of view of contaminants, because if you want to drink this water, well, your breath is not going to be very nice with hydrogen sulfide and sulfur dioxide. You have ammonia, is going to be pretty rough on your throat. You got mercury, magnesium, all sorts of things. So we're going to have to be careful once we obtain this water and be able to clean it up. But from the point of view of resources, this may be one of the few sources of nitrogen which is going to be needed in ammonia for plants and growing things like this. So it's both a curse, but also a blessing. So the other thing that we found is location, location, location. Just like on Earth, it is important to know where you're landing on the moon. These missions not only found these permanently shadowed regions where the water is, but as important are the rims of these craters. These were called by a very romantic French scientist in the 1800s, Flammarion, that called it the peaks of eternal light. Well, it's not eternal light, but if you're in the poles, if you're in the mountains or rims, you get light most of the time, about 93% of the time, whereas the rest of the moon is, you gotta wait 2 weeks for this. So this is where you can have solar power, where you can have communications, and that explains why everybody, the US, Russia, China, India, Japan, everybody wants to have a place in the South Pole. This is going to become prime real estate. This is like Mount Vernon Country Club in the Golden area. And you can already feel that this is going to create tensions. Everybody wants to live in the same place and have access to the same resources. So we're going to see later how we're going to handle that. Also, it's an opportunity to use the solar energy and beam it down to the bottom of the crater. And the moment that ice sees for the first time, light is going to start sublimating. It turns into a gas that we can capture on a tent, and we can go ahead and collect that material. So this is the idea that we have about the South Pole or the North Pole. About 3% of the Arctic circle of the moon has water ice stored in these deep craters that you find permanently shadowed regions, which is going to be important for a variety of applications. Now, you look at it, and I'm sure you're wondering, well, how much water is that? Is that oceans? Is that lakes? It's about 100 million to 1 billion metric tons estimated. 1 billion metric tons. Wow. You know, is that like Atlantic Ocean? Could be one of the Grand Lakes? Is it a river, a creek? Well, it's equivalent about one of the lakes, but the tiniest of them, the Lake St. Clair. That's about how much water is on each pole. If I put it in terms of Colorado units, it's about 2 to 3 Lake Dillons per pole. And you're going to say, well, that's not much water. It's not much water if you want to keep billions of human beings alive, but it depends on who the customer is or what the purpose is. If you were to use that water for a crew of 2 or 3 people, obviously there's plenty of it, and you can recycle almost 96%. But it's most important because you can split water into hydrogen and oxygen, the most energetic fuel that you can find. And if you were to put this in terms of how many rocket launches are available for all the water that you find in each pole, it will be equivalent to about 1 shuttle launch per day for the next 2,200 years. So that tells you right away, well, that water looks interesting. And because it's going to be of much use. I'm going to make another comparison that is going to sound very difficult to comprehend at this point. The amount of in each pole is about the weight of the estimated reserves of oil in the Gulf of Mexico. Now you're going to say, why are you comparing oil with water? They don't mix, they don't get along. What's going on here? Just hold your thoughts. I'll let you know why I'm doing this. So these are the elements that we have on the moon. That's great. We have volatiles, water, rare earth, metals, everything. But let's keep going. There's more to the solar system than this in the near future. So let's now travel to those amorphous rocks that are all over the solar system. These are the so-called asteroids. And you find them in all sorts of shapes and sizes. You go from about a meter, very regularly shaped, to almost a spherical dwarf planet like Ceres that grew to the point that almost becoming a planet. These are the asteroids that we learned probably in high school, that they are in this well-behaved band between Mars and Jupiter, the asteroid belt. But nature is not that well-behaved. You know, sometimes they bump into each other, there's impacts, and they end up floating all over the solar system. You may look at the skies at night and you may think, oh, it's beautiful out there. Well, there's rocks all over the place. So you have to be very careful when you travel. But some of those rocks, these white points, end up very close to the orbit that the Earth has around the sun. So here's the Earth going around the sun, and a lot of them are trapped around here. These are the so-called near-Earth objects, and the interest about this is because they're closer to us than the asteroid belt. You know, you can travel to them easily and extract their resources. Now, what type of resources are on the asteroids? Well, let's take a look at them. People that study asteroids have like 30 or 40 different classifications. We're going to concentrate on 3 from the point of view of resources. They are the type C, it's called type C because are carbonaceous objects. This is one asteroid in which we landed, and just last year we returned the samples. You probably heard in the news that they had a hard time opening the capsule there, but we finally got a chance to see them, and indeed, they contain carbon, they contain up to 20% of water. So this could be very interesting material for rocks that are all over the place. Then you got the S type, that stands for silicaceous or stony objects. Here we start seeing nickel and iron. This is a visit that the Japanese did to the Itokawa asteroid. And then there's the metallic types. We have never seen one up close. There's a mission right now called Psyche that will be there in about 3 or 4 years. And for the first time, we get to see a metallic object in which not only you have nickel and iron, but you have the noble metals, gold and silver, and you have the platinum group metals. You got platinum and iridium and rhodium. These are very heavy elements. That this is because the asteroid grew to a point that every heavy element went to the core, and then it got bumped, and what's left is the core, the very heavy-duty core. Now, some people come out of my talk and say, well, he was talking about what types? S or T or S or C. Let me give you a hint on how to remember this, even years after you left this. It's CSM, Colorado School of Mines. So it's a shameless advertising, but that's the way I remember. That's the way my students remember it. What is it? Colorado School of Mines. Okay, CSM. Good. Now, how do we know about them? We know because we have observatories on the ground that can see this, but we can also have thousands of meteorites that have fallen into our hands. These are rocks from asteroids that we have in our hands, and that's why we can tell what they are. In fact, I have here one in my hand. It's one of the metallic types, the so-called called stony. They're called stony and iron, but the iron meteorite, this comes from the core of asteroids. This is the heaviest rocks that you can have in your hands, and you can welcome to to hold it when we're done. But these are remnants from the core of asteroids. And so that's how we know about what they're made of. Good. All right, so what do we have? We have the intangible resources. We have all the resources from the moon that we looked at, the metals, the water, the earth, and the like. Do we keep going? Well, I guess and also we have the asteroids now. And now you know the different types. You got the C and the S and the M. Well, let's go to one more destination, and let's fill that hole. Let's go to the most interesting planet that we have close to us, that is the Holy Grail in terms of resources other than Earth. This is Mars, Mars in which we have explored even probably more than the moon. We have all sorts of spacecraft going around. We have rovers that have been roaming around different parts of the planet. And we have found that Mars has all the right metals that the moon and the asteroids have. And it also has plenty of water. You can even see it on the poles as ice. And it has carbon dioxide on the atmosphere. And the moment you have carbon, you start thinking hydrocarbons, fuels, plastics, everything else that we use on Earth. So Mars holds a lot of potential interesting resources. So here you have all the resources that I just mentioned. I'm not going to go any further because this is what we believe is going to happen in the next 10, 15, 20 years. And I keep telling my students, this is within your professional life, not mine, but theirs. I'm not going to go any further. There's oceans in Europa and there's hydrocarbons raining in Titan in all places, but this is as much as we're going to go. And these are natural resources, but believe it or not, they're human-made resources in space. And this is all the trash that we have sent for 60 years. This is the space debris, which is becoming a real problem because these things are hitting satellites, are destroying satellites. It almost hits the space station. It has to actually change attitude every once in a while. And so there's a big movement now. Just a few months ago, there was a Russian and Chinese satellite that they exploded, and they have thousands of pieces that can hit another one, and those can become millions of pieces, and this have become a big problem. So the issue is how you can capture and burn them in the atmosphere. But don't do that. This is a resource. Why can't we just recycle it? You have aluminum, you have titanium, use it as a resource. So once you go into space, you have to become extremely resourceful and see what you can use, because we have already spent money doing this. So okay, we have all these resources. So the question might be, you look at all of them, is which space resource is more valuable? So I'm going to ask you, which space resource do you think is more valuable? And I'm going to give you some options here. Noble precious metals like gold or platinum, metals, iron, aluminum, titanium, oxygen, water, solar power, helium-3, location, space debris. Who goes for precious metals? Wow. Nobody likes jewelry or anything like that here. Very interesting people here. Okay. Metals, iron, aluminum, titanium. Good. That's for spacecraft. Oxygen. Yeah, you need to breathe, obviously. Water. Wow. People are thirsty. There's some water up in the back there. Solar power. God, people are cold. All right, good. That's important. Helium-3. Maybe in the future. That's correct. Location. It's important to things up and close. Space debris. Yes, somebody thinks that we need to clean it up and use it good. Well, this is a tricky question, because I didn't ask you if this is in the near term, the medium term, the long term. Are these resources that we want to bring to Earth, or we can just use them in space? If we were to see the resources that we have on Earth, even though you have probably these gloomy talks that you may have here that we're running out of everything, there's still plenty of resources on Earth. We have barely scratched the surface, literally. There's plenty of resources. We just need to do more prospecting. We need to probably drill deeper. And I just heard from Mary of a big tool that is being tested to actually drill miles down. And maybe only when it becomes so deep, we're causing too much environmental damage, we're using too much power, maybe then, if we have an infrastructure in space, we can start thinking about bringing resources to Earth. But not, it's going to take a while. So how about using the resources in space? And why? Well, if you think about it, we have sent thousands of rockets for the last 60 years to space. And everything that we have sent to space, every satellite, every human consumable, every bolt, every nut, everything comes from Earth. We depend 100% from Earth to explore space. And that's obviously not an efficient, that is not a sustainable, that is not an economical way to explore. At some point, it's going to limit us. And in fact, that's where we're feeling right now, that it's only so much that we can do from launching things from Earth. And that's because of a big force called gravity. Gravity that keeps us firmly on the ground, that it is really hard to overcome. And that's why it's so energy intensive to launch anything into space. And it's also very expensive. Let's just take a look at any rocket on the launch pad. I don't care what it is. It's the Saturn V that took us to the moon, or it could be the new shiny rocket from NASA that is going to take humans to the moon again in 3 years. Or it could be SpaceX, one of Elon Musk's rockets. I don't care what it is. 90% of that rocket is fuel that is used to launch that tiny 10% when you have your satellites, 2 or 3 people, and 10% includes the structure and the pumps and the tubes. You're lucky if you can send 2 to 4% into space. That's a lot of energy. And that's just because the gravity that has to be overcome. That's not a very efficient way to do things. It's also very expensive. You want to launch something to low Earth orbit, just 400 kilometers above us to the space station, about 5,000 kilograms, $500 a kilogram. You want to go to the moon, 10 times more, 50,000. You want to go to Mars, it's about $500,000 to launch something like that. You want to launch if you need some water, you want to launch this bottle, this is about $250,000 to send it to Mars. Well, that's not a very good idea. And that's just material. You want to send humans, multiply that by 10 because we are a very special species to keep alive, so that's very expensive. And so you're going to say, wow, that's an exponential rising cost. Yes, it is exponential because the equation that controls rockets, the rocket equation, is exponential. It was designed by Tsiolkovsky in 1903. He was a high school teacher in Russia that came up with this equation, and you don't need to go into the mathematics. What it tells you that you want to go further and further, the amount of fuel that you have to bring just goes up exponentially to the point that at some point you just cannot launch this huge rocket. Tsiolkovsky was able to see in 1903, as a high school teacher just doing math, this is the power of thinkers, without doing any experiments. At the same time that the Wright brothers are trying to lift from the ground in Kitty Hawk, he was able to see the problem that we're going to have in the future. And he said, we're going to need space resources. He even said in one of his books, he said, a rich and inexhaustible source of material, in this case, he said, for establishing colonies beyond the Earth orbit lies in space. So he was able to foresee in 1903 the power of resources that we can use without having to send things from Earth. And this is a very inefficient way to travel. We don't do this on Earth. On Earth, if we decide that this weekend, let's all take a trip. Yeah, why not? Let's actually drive from Denver. Where do you want to go? Let's say, let's go to New York. All right. Let's drive, everybody, let's hop on our cars, go there, stay about a week and a half, 2 weeks, and then come back for work or for retirement if you want to keep going. If we're going to do this, we're not going to carry with us all the fuel that we need and all the food and all the drinks, let alone all the chips that you need along the way. That's going to cost you a lot. That's a lot of weight to carry, and just a cop may stop you if you drive like this. No, what you do is you stop in gas stations and you pick up food in convenience stores. And if you go to New York, yes, home food is great, but by the time you get to New York, it may not be that good. So might as well just get some good Coney Island hot dogs there that are fresh, hot, ready to go. This is what we do on Earth. And that's exactly what we want to do in space. So when the question is, which space resource is more valuable? Is that resource that allow us to live off the land. Don't bring everything with you. Don't bring all the fuel that you need to go all these places. Refuel in space. You got all these gas stations out there. Don't bring the bricks and mortar to build things on the moon. This is what's called in our field, very fancy term, in situ resource utilization. It's just using the resources on site, local resources, without having to bring it. And that opens up a lot of possibilities. So if you look at all these resources, one of the ones that stand out, and most of you were right, is the same resource that we look for everywhere we go. Good old water. Water that you can drink, fine, but again, we can recycle a lot of that. In fact, if you go to the space station, if you see sometimes the astronauts floating around and drinking, they're drinking their own sweat and their own pee, because they can recycle up to 96% of that. So that's not the case. The beauty is that you can split it into hydrogen and oxygen, the most energetic rocket propellant. So think about what we can do. Now we're on the moon. We have a base on the moon. We have the water right there. It doesn't cost $50,000 per kilogram to obtain it. We can split it into hydrogen and oxygen, and we can use it to bounce there to other places, and we can even use to export it. In fact, it's cheaper if we were to have the water on the moon to send it from the moon, which is 350,000 kilometers away, all the way down to the space station, which is just 400 kilometers above us, that send it from Earth, because you're launching from a place with much lower gravity. You can then put it in fuel depots and you start recharging in space. You can start creating a propellant refueling network in space. You can refuel things that now are thrown out, or satellites that go dead. You can obtain water from asteroids and bring them to these fuel depots and really open up the possibilities. You start lowering transportation costs, and just like on Earth, when the moment you lower transportation costs, you open it up for everybody. That's what has been impeding us from doing that. This is why only a few countries have gone to space. Only about 600 people have reached space. You lower the transportation cost and you start seeing what you're seeing right now in terms of tourists going into space and the like. And that is why the water, if you split it into hydrogen and oxygen, is being called the oil of space. That's why I made reference to that strange comparison. Because just like oil did for us here on Earth, that opened up transportation and open up commerce and everything else, that's what water is going to do for us. It's a non-renewable resource, but it's everywhere in the solar system, and we're going to have to be careful and we have to act responsibly. But that's some of the things that we're going to talk about in terms of what are the concerns about resources. What else can we use there? Well, use the lunar regolith for construction. Don't bring the bricks and everything else. Just use it to build things using 3D printing or whatever you want to do. Extract the metals for tools, for spare parts. Use whatever is available for you. That's the whole point of space resources. It's not to bring them to Earth. It's about utilizing it wherever you're going. And so here we go to the second aspect that I mentioned. Okay, we already have seen what are the possible recoverable resources. Now let's look into what technologies are being developed at this point in order to identify and to extract them and to utilize them. So this is where the concept of space mining comes in. On Earth, we have been very successful on mining because we've been doing it for thousands of years, because we have four important things. We know how to develop things under normal gravity. It's the only gravity that we know. We develop things under terrestrial environment. We know our temperature. We know that we have an atmosphere. We have plenty of labor, and we have plenty of power. But if you want to go to the moon or Mars, all of those things are going to change. This is the big challenge. All of a sudden, your gravity goes to 1/6 on the moon, 1/3 of gravity on the Mars. You are on a vacuum, so anything, any lubricant, any water you put is going to evaporate. You are under very extreme temperatures. On the moon, you can go from minus 200 degrees to 100 degrees in just a few meters. As you can see there, there's not much labor, and so we're going to have to use robotics and automation. And the power, we're going to have to figure out what we have available, solar power, nuclear power. And so here are some of the technologies that have taken into account these type of challenges to design. Excavation. At first, about 15 or 20 years ago, when we started doing this, we started looking, well, okay, this is the type of machines that we excavate here on Earth. Huge, massive machines. Bucket wheel, bucket ladders, backhoes. Well, on Earth, we're going to have to send things that are a little bit smaller because we cannot send things like this. But we started imitating what we do on Earth. So we had the same thing, bucket wheels, bucket ladders, backhoes. We even have some astronauts still working with some backhoes there in Utah, in Nevada, I think it is. But then we started thinking, well, this is just imitating what we do on Earth. Why about designing things that are specifically made for the moon? And here's where this concept comes in. Here's an excavator that doesn't look like anything you find on a mining field, but it can work at 1/6 gravity. It has all the enough traction. It doesn't have any lubricants. It's light. It's completely robotic. It can excavate and transport at the same time. And if one goes bad, you can send a swarm of this instead of sending a huge machine. So it's been designed for lunar purposes. And in fact, it's going to be tested in about 3 years in the lunar surface to see how effective it is to work under those conditions. Once we excavate the material, now it's time to extract. And let's extract water, which is an important one. Here, there was a design of a way to mine that we don't use here. It's called thermal mining. What is thermal mining? I talked about this a little bit. What if we can just use heat coming from the sun, redirected to the bottom, and there you can have water that starts sublimating, become a vapor. You can trap it inside a tent, and then you cold trap it in a place that is very cold, and you got your water without having to drill or do anything like that. So that's one of the techniques that has been proposed. In fact, we tested it in our lab at Colorado School of Mines, and we started looking at how do we replicate this. First of all, you're in the moon. It's a vacuum, so we use a vacuum chamber. You're going to be very cold. We use liquid nitrogen down to minus 200 degrees Celsius. Then we use simulants. These are things that we learned from the rocks that came from the moon, and we can replicate it with material from Earth, mixed with ice and with some material. And afterwards, I'm going to show you some of this. I have simulants for the dark spots on the moon and the white spots. This is not beauty product, but if you want to use it for that, that's fine. But I can show you some of that later on. We even make simulants of Mars. It's a little bit reddish. And these are things that we make at School of Mines, and we actually send it to companies and NASA centers so that they can use it. And then once we have all those ingredients, then we start heating it up with the same amount of heat that they will feel on the moon. And in that way, we can extract and look at how much vapor comes out of that. So that's extraction. How about construction? We talked about 3D printing, how we can make things out of the lunar regolith. Well, interesting enough, the private sector is joining this, saying, we know about this. We don't have to wait for NASA to do this. And in fact, one of the companies that started doing this was the company that had the first permit of a 3D printed house in the US. This is the first 3D printed home that they built in a couple of days. And now they're building entire neighborhoods in Texas, military habitats, Guatemala, Mexico. They're building all of this. It's a company called Icon. And they said, well, if we do this on Earth, why not use that in space? And so now they have, they're working very closely with NASA, and they have designed a 3D printing machine that can be worked on the moon and Mars. You're going to see here a big 3D printer that they use in NASA Johnson Space Center to construct a habitat. So they introduced the large 3D printer the large 3D printer machine, and in a few days, you can have a complete habitat on the moon. And in fact, NASA is now recruiting people to live there for 1 year to replicate how we would like to live on Mars. And this is just from technology that we have here on Earth. So that's some of the, that's exactly, that was happening in 60 minutes. And the CEO of the company, he was one of our students of Space Resources. In fact, he called me about 5 years ago and he said, hey, you know, I'm making these 3D printed homes here. Can I join your program and see how I can make it on the moon? I said, oh, that sounds like a crazy idea, but come on in. And he took our courses and all that, and then it started growing rapidly in terms of his terrestrial business and his space business. He became the Time Entrepreneur of the Year. He's now $1 billion or so company that is doing things both on Earth and space. So it's a fantastic story. So you're going to ask, okay, what are we doing? These things are we preparing for on Earth? What are we doing in space? Are we doing anything about resources? Well, interesting enough, today there's a rover 200 million miles away from us, the NASA Perseverance rover, that has some instrument on board that is ingesting carbon dioxide and is converting it into oxygen. This is the very first resource that has been produced in space, and it actually happens to be on Mars. That means you can go and there's a tank of oxygen waiting for you to breathe or to use it for propellant or whatever you want to do. It's a demonstration. It has to be scaled up if you want to have a crew there, but it's a demonstration of what's to come. Most of the work that is happening now, and it's going to happen between now and 5 years, is the first phase of mining. It's the prospecting. You want to know what the resource is, and then later on see how you extract it. So the moon being so close to us is going to be one of the first destinations. And here's something that is going to happen this year. You're going to hear about a mission called Prime 1 that is going to go to the moon and become the first mission that is going to be robotically drilling on the lunar surface. It's going to go to the south pole of the moon. And now you know why, because that's where the water is and all that. So what it's going to be doing is going to be used the first drill from a company, another private sector company called Honeybee Robotics, and it has a spectrometer. This thing measures what is you're extracting. So it's going to go down, drill about 30 centimeters, and then it's going to pull up some of the material that can be analyzed to see what's in there. Then it's going to go 60 centimeters down. It's going to pull it out, and then it's going to see what's available in there. And eventually it's going to go down about a meter in this region where we think that there may be all these resources that I mentioned. And what this instrument is going to be able to measure is obviously one of the most important elements, which is water, but also hydrogen and carbon dioxide and nitrogen that all will be needed. Next year, with the same drill, there's going to be another mission from NASA called Viper. And there you're going to have the drill, but it's going to be on a rover. It's going to land close to the lunar poles. It's going to go down to the permanent shadow craters. It's going to start drilling there in several parts because you want to know how widely distributed is the water or the nitrogen, the carbon dioxide. And you're going to start extracting some of the material from a place that we thought it was bone dry 50 years ago. And so the U.S. is not alone. These are the prospective missions that are ongoing and they're going to be happening soon. You got Canada. You got Korea. South Korea is already having a spacecraft going around looking for water. India has a spacecraft that landed last year. Japan and India are going to join forces for a lunar mission to look for water. The European Space Agency is going to prospecting for water in about 2 or 3 years. China has 3 missions planned already to look for resources and then bring samples to Earth. Russia has another 2. So you can see the competition that is happening just to prospect and what's going to be happening later on. And so this takes us to the last stop. We have known the recoverable resource, the technology to recover. Who cares about this? Who's the customer? You need a demand in order to use these resources. Well, space agencies obviously are very interested because if they lower the cost and the risk to do this, they will actually do whatever it takes and buy it from whoever has it. 50 years ago, when we started doing this, NASA was the only one. It looked a little bit like science fiction, maybe in the future. But then it became obvious that resources were going to really help in exploration for them. And in 2016, things changed. And it came from a country that you just wouldn't believe. It's one of the tiniest countries in Europe. It's Luxembourg. Luxembourg that has a very apt financial way of looking at things. And they said, this is the future. Luxembourg in the 80s, it becomes a financial capital of Europe. In the 1990s, they bet on satellites. When the world was saying, why do you need more than 3 channels of TV? Well, Luxembourg invested heavily and is one of the largest providers of satellite imaging. And now they're saying we're betting on space resources. And after this happened in 2016, now you got all sorts of space agencies. You got Russia, you got the European Space Agency, the Canadians, the Indians, the Japanese, the South Koreans, China. You got the United Arab Emirates, Australia, all of these agencies saying we can actually have expertise to work in parts of this and make this happen, and maybe collaborate, some of them, among each other, and make this happen. When this was realized by the United States, and they started seeing the interest from different countries and companies, they started saying, it's no longer the realm of NASA. You need other government agencies to get involved. And now you have the United States Geological Survey that say, we've been doing this for hundreds of years here. Why not use our expertise to locate resources? The Department of Commerce that now has its own space administration, seeing how this is going to be a commercial activity. The Department of Energy that is developing its space strategy, how to use nuclear power again, how to do solar power. Even the Department of Defense is now getting involved because they're seeing that we're going to have economic assets in space. Who's going to protect that? And other things that may come as the competition starts building up. And it's not just the government. Now you have aerospace companies realizing this is an opportunity. Companies like United Launch Alliance that in 2016 said, you can give me propellant in space and I don't have to launch it. I will work with it. And I'm going to build my spacecraft to use hydrogen and oxygen. Lockheed Martin, same thing. Their lunar lander is going to be working with hydrogen and oxygen. You got companies like Boeing and Northrop Grumman now building the fuel depots in space. So you can start seeing how this is becoming of importance. You have new companies like SpaceX that is offering rides to NASA to the moon. It's going to be one of the ones that are going to be used. Blue Origin that also is going to be working with Lockheed Martin to generate these lunar landers. And interesting enough, all of these companies have presence in Colorado. That's why Colorado is such an important sayer in terms of space resources. Even Blue Origin has some offices here. And so you start seeing now that the competition is going from the Soviet Union and the United States in the 1960s to getting really crowded on the moon. Now you got China and the US, and you got companies like SpaceX and Blue Origin, everybody trying to get this, and use it not just for exploration, but for commercial purposes. And it's not just the large companies. You have more than 100 companies that have emerged in space resources in what we call the space resources value chain. So you have startups and mid-sized companies and large companies that have never worked in space that are now working on this, on all aspects. Who's going to be doing the prospecting? Who's going to be drilling and construction and exploration? Who's going to provide all the infrastructure? We need power. We need communication. We need transport. You have companies that you never heard that were in space. Caterpillar, Schlumberger. You got Rolls-Royce, Honda, looking at vehicles that are going to be moving around. And they're seeing an opportunity here to become both providers and also clients for this. So you can see now that the interest is worldwide, is from the private sector, is from the government, and all sorts of things of space resources. It's exciting. But you may be thinking now, is this legal? I mean, can I set up my operation on the moon and extract the resource and start selling it? Are there any rules about this? Well, the only rules that we have comes from 1967, from the Outer Space Treaty, that was signed by about 120 countries at a point when everybody said, this is crazy stuff. It's only the Soviet Union and the United States that care about this. I'll sign it. Good. It was a really good treaty. Actually, it came out with very important principles. Article 1 talks about the exploration and use of space shall be the common province of all mankind. You can start seeing very altruistic things that everybody can use space, so big that we don't have to worry about it. The second article says that it prohibits the claims of national sovereignty. That means no country can own a planetary body. You cannot own the moon. You cannot own Mars. So it was very clear. By 1979, the Moon Treaty came along. At this time, people are saying, well, there's probably more to space than just 2 countries going at it. And only 19 countries signed it. And none of the spacefaring nations, no China, no the US, not Russia. And so the problem is that this is very nice language. But when the time comes to say, well, I cannot own the moon, that's fine, but can I extract the resource, clean it up, and then leave the place? Just like we have claims here for mining or the seas, the law of the seas. And that's where the language becomes a little bit fuzzy. And so now what has happened is that countries have taken matters into their own hands. And it's not only the legal aspects that are important. Is this fair? Is just for the big superpowers, or is everybody going to benefit from the resources? It says here, it shall be the common province of all mankind. All mankind has to benefit from resources from space, and not just a few. And so what happened in 2015, starting with the United States, they passed the Space Launch Competitive Act of 2015, was passed by the Senate, by the House, by the President signed it. And it says very clearly there that a United States citizen or company engaged in commercial recovery is entitled to space resources, to possess it, to own it, to transport it, to use it, and sell it, as long as it fulfills the international obligations of the United States. So that means they interpret in the treaty that, yeah, I don't own it, but I can probably use it. And as long as you're a company in the United States, you're allowed to do that. The following year, Luxembourg followed suit and became the first European nation to offer a legal framework for space resources. Same thing, if you have a company on Luxembourg, you're allowed to do it. Then following year, the United Arab Emirates followed suit with another space law. And then Japan in 2021. But these are individual countries saying, if you come to me, then it's okay to do it. But what about the rest of the world? And so what happened is that non-governmental organizations started saying, we have to address this issue. And it started in the Netherlands, The Hague, that came up with the Hague Space Resources Governance Working Group. It gathered about 35 different countries to talk about the importance of space resources and come up with building blocks of how is that we should do things in space. We should probably have safety zones. And how is that we going to distribute the benefits of this? It finished its work in 2019, and that work went to the United Nations, to the Committee on the Peaceful Uses of Outer Space, and specifically to the United Nations Office of Outer Space Affairs. So you can start seeing why it's not just world affairs. That things are becoming interesting and challenging in outer space. So now the United Nations has a subcommittee talking about this, and in fact, they met a couple of weeks ago in Luxembourg to talk about all these things. Now, as you know, and some of you have been diplomats here, things in the United Nations take time, a long time. And so countries are desperate now to get started with this. See, is there any other way that we, not just bypass the United Nations, it's fine, whatever they say, but can we act in a way that we can assemble a group, a club of people that agree with the rules, and we can start doing this? The United States started doing this with what's called the Artemis Accords in 2020, in which 9 countries agreed to play by some rules. We're going to register every launch. If we're going to go to a site, we're going to say, where is that we're going to do this? And we're going to inform people what we're doing. So we have people like here, like Japan and Luxembourg, and United Arab Emirates, Italy, Canada. But it has become so popular that almost every month there's a new one coming. In fact, right now, this is up to April, 38 countries. The last 2 countries were on Monday, it was Switzerland, and yesterday Sweden joined. Now you got 38 countries that are now saying, let's all belong to this, and once we agree on rules, then it's all fine. We can all play by this, and we all can benefit from that. Well, that's great. But some countries may not want to play with this club. So at the same time that this happened, all of a sudden, out of the blue came the International Lunar Research Station by China and Russia. And they said, we're creating our own lunar station. Do you want to join? Whoa. All right. And that has grown now to 8 countries. And now you can see the usual suspects and some not so usual suspects. You got China, you got Russia, you got Pakistan, Azerbaijan, you got Egypt, you got South Africa, you got Venezuela. These are countries that are aligning on one side. Once there are 2 that are now have applied for this, which is Turkey and Thailand. Some countries are hesitating. In fact, the UAE tried to join both, but decided might as well stay with the Artemis Accords. Because you start seeing some conflict here. Because both are going to the same place. They're going to the South Pole. They're going to the same, the permanently eternal peaks of eternal light, and this is going to probably create some conflict. So this is becoming an issue that has to be solved also as far as the science and technology. At the same time, there's a concern about the fairness of this. Okay, it's not just the big superpowers. So what do we do about it? So again, Colorado comes to the picture. There's a foundation that decided we have to reach out to the rest of the world so they know that this is happening so they can be part of this. So the Secure World Foundation from Broomfield, Colorado, is an organization, is a foundation that talks with governments, with companies, and tries to have a peaceful use of space. So they talk about all things about space debris and resources. And they organized the first workshop in South Africa, in Pretoria, in which they brought 10 African countries to start talking about this. For them was the very first time they have heard not just the space resources of space, the countries that have never participated in space, but they're saying, look, we have quite a history of mining. We can actually get involved in this. NASA may be really good at rockets, but they don't know a thing about mining. So maybe there's an opportunity for us to work on here. Not necessarily just receive a tax that comes from sharing the benefit resources, but actually getting involved. And that's the whole point of bringing people along. Then COVID hit, and other organizations started working on this. The Space Generation Advisory Council is a group of students and young professionals up to 35 years old. I cannot belong to that anymore. But they can talk directly to the United Nations about this. And this was done by the chapter in Venezuela that brought along Venezuela, Argentina, Chile, and Colombia on a webinar to start talking about how is that Latin America can become involved in this. So you can start seeing how countries say, we can be part of this. We can get our youth working on this. We can get our companies working on this. And there could be an opportunity. Once COVID left, then the Space World Foundation hit it again last November. And this was in South Korea when there was a perspective for new entrants of space exploration programs. So these are countries in Asia, but also there were countries like Poland and Mexico that started participating and learning about this and see how they can get involved. And they're going to do it again in November. There's going to be one in Brazil that is going to bring South America along. So you can see now the impetus to have all these countries participating so that everybody benefits from space resources. So what I have tried to do is give you an idea of how space resources promises to give us not just further exploration of space, much better exploration than now, because now it will lower the transportation cost. It will be able to have larger payloads, explore much widely. We can actually stay in planetary bodies or on the moon, not just be there for a couple of days. We can refill satellites. And not only that, we can start commercial activities in space that will truly bring space into the global economy. It will be up to each and every one of us here on planet Earth to learn from the thousands of years that we have extracted and benefited from resources, and we keep being benefited from resources, to learn of all the good things that resources are giving us, but also all the bad things that come along. We have wiped out entire civilizations. We have really damaged the environment in doing this. Now that we're starting anew, let's try to do it now in a, not just in an effective way, but in a fair, in a responsible, in a sustainable way, so that we can really benefit from the resources just like Colorado benefited back in the 1800s. And so that we can also fulfill the dreams of those that we were able to foresee the power of space resources. Like a good friend, our high school teacher from Russia, Konstantin Tsiolkovsky, that had that equation, that he saw it in that exponential. He said, there's no way that we can continue exploring if we don't use space resources. That same year, he said the following. He said, the Earth is the cradle of humanity, but humankind cannot stay in the cradle forever. Let's keep working on space resources so that we fulfill its promise. Thank you so much.
You're going to split oxygen and hydrogen, but that takes as much energy as you get from the fuel. Where are you going to get all the energy to split it?
Absolutely. You need energy to split it. Use what you have there. You got solar power that is for free. You have, now we're talking about nuclear power to bring in nuclear modules that can operate on the surface of the moon that will provide that energy so that you can use it. But you're absolutely right. You need energy. And that's one of the big things about space. You need low mass, low power, and low volume in order to make it economically feasible. Yeah.
Where are we with hydrogen energy here?
On Earth,
On Earth.
on Earth, hydrogen became a big thing about the hydrogen economy, and now everybody's going electric. I think there's still a push for hydrogen, and in fact, companies, oil and gas companies, have been interested in resources because of hydrogen. Shell, for example, they say they're moving to the hydrogen economy, and they're saying you're probably going to need our help on this. They slowly getting into the possibility of doing this, but hydrogen may become an important thing on Earth and in space. Yeah.
Next question, Scott.
Yes. I really enjoyed your presentation. You're a great speaker.
Yes.
And it takes me back 65 years when Sputnik went up. But I guess the real question, you probably answered it, but I missed it. Why are we doing this and who's going to pay for it? I'm all in favor, but why? We haven't explained the ocean, but we're going for space. And I think that's great. But the question really is, how does humanity benefit and who pays for it?
Very good. And that's why I said this has to be a customer and it has to be economically feasible. So why doing this? If you can lower transportation costs, look what we have done just launching things with how costly it is right now. If you lower transportation costs, all of a sudden, and you're starting to see that now, Elon Musk has reduced the cost of transportation, and you have these mega constellations for all sorts of things of communications. That once you have presence on the moon, there's many things that will open up that we may not even know what it is. For example, if you're on the moon and you have humans there, crews of 5 or 6, at very cold temperatures, you may have a data center that needs very cold temperatures. Now we're using a lot of energy just to keep data centers alive. Can you put one on the moon and be able to use that? Can you use it for other purposes and refuel in space? So that's what's incentivizing the companies. They still want to see who's going to be first. And yes, the space agencies want to be first because they're going to be the ones, the first customers, like anything else. Railroads and airplanes and lasers, always the government will step in, put the infrastructure, and once you lower the cost, then the rest will come. So you have to lower the cost. You're absolutely right. But once you do that, then you open it up. Even tourism. People will pay for going strange places on Earth. They will pay to go to the moon. So tourism may be one, and all sorts of possibilities. Maybe Mars, there's not a commercial incentive for doing that. But what's called cislunar space, the moon and asteroids, this is in the neighborhood and can really benefit us in large ways.
Thank you. Any other questions? Oh, thank you. So I was not comforted by the fact that we all haven't gotten on board with agreeing about landing places. So if China and the United States decided they wanted the same resource at the same time, how would that work?
That is a very good question. And in fact, I acted as a technical observer for this United Nations Outer Space Affairs Office. And there, if you're in Europe, you can probably be in the same place where Chinese and US and everybody is. Here in the US, it's very difficult. But over there, you could see the Chinese not disagreeing with the Artemis Accords. They're saying, we just want to do it our own way. But at some point, there's going to have to be an agreement. And if everybody wants to land in the same place, I'm sure there's going to be diplomacy involved in this, just like what happens on Earth. I don't think, hopefully, that if the United States lands, now China is going to land right next to them. There's going to have to be what's called safety zones to protect equipment and to be able to say, well, this is what we can extract and what you can extract. But who knows? It's going to be possibilities of conflict, and you can start seeing it. That's why I think it's important for a group like this to see this type of conflicts. You had a lecture the other day about U.S.-China relations and the tensions that you have. Wait to see what's happening right now. And China is moving very quickly on this. And so at some point, yes, they may talk in very rough terms, but I think they're going to have to agree for the benefit of both of them. Because at some point, there's going to need power. Somebody mentioned we're going to have nuclear power and solar power available. Can we all use it? Can we all share it? Can a company sell it to different countries and we all benefit without having to everybody have the same infrastructure? So at some point, just like we do on Earth, China and the US actually collaborate on prospecting for certain materials, and then they compete hard once the extraction comes in. But there's probably ways that everybody can benefit. Let's hope.
Absolutely fascinating. As a diplomat, though, I really worry about these interactions of different countries, companies, and so on. What about weapons? One of the earlier treaties said no weapons in space.
Correct.
Are these new agreements revolving around no weapons in space?
That's it's established by the Outer Space Treaty, and every country that signed it, China included, has to abide by this. No weapons in space. Are you going to not do it? I don't know, but there's no intention. Like, for example, the Space Force is talking about being present on the moon and helping with infrastructure, but no word about military use. Obviously, if there's a conflict, who knows what's going to happen. But it's in the Outer Space Treaty, and you sign it. The only way to monitor that or to react to that is what happens in the United Nations, the name and shame, that if somebody does something, the whole world is going to point fingers. And as a country, you don't want to do that because China is going to depend also for other countries. So we're hoping that the same diplomacy that applies on Earth hopefully will apply in space. And I don't have to tell that to you because you've seen that being violated probably several times.
It's interesting as you were talking about timing and how quickly this seems to be developing. What do you see as timeframes for larger, real commercial resource extraction or development in, like, say, the moon? Are we looking at a time horizon? You said your students, it'll happen, is it 10, 20, 30 years?
Yeah, what I mentioned is that from here in 5 years, you're going to have a lot of prospecting. You need to know that you have a proven reserve. In fact, when we talk to mining companies and oil and gas companies, 50 years ago, they just would shut the door and say, these people are crazy, this is science fiction. And slowly they started opening a little bit, and they say, well, okay, bring me a business plan, and we'll talk. In fact, we conducted a big thing spearheaded by School of Mines and United Launch Line and other 25 organizations, looking at how much would it cost to extract water from the moon. Everything, storage, maintenance, transportation, everything, and came up with numbers and show it to mining companies. This is the amount of money that you need. This is the amount of years that you need. It was about $3.5 to $4 billion in 10 years with a rate of return about 19%. They say, well, 19% is not a really good one, but we do this all the time. $3-4 billion, we do it all the time. You just need to tell me three things. Tell me that it's a proven reserve, tell me who's the customer, and tell me if it's legal. Then we'll get in. And so when you talk about the timing, the first thing is we need to prove that these are proven reserves. This is the amount of water, this is the concentration, the distribution, how accessible it is. Then you're going to have at the same time technology demonstrations, how to excavate, how to drill. Once you prove that, then you may start providing that to space agencies in very small quantities. Then come the scaling up. That's going to take probably a little longer. To provide propellant for a rocket to take off from the moon, that's going to take an infrastructure, and we're talking 15 years from now or so. That's going to have to prove that it's a real business plan. Like the gentleman in the back said, if it doesn't make economic sense, it may not happen. But if there's customers and they're willing to do it and they see that there's a profit to be made, you'll see that accelerating. And that's what mining companies say. Technology is not an issue for us. It's other things, the economic part, the legal aspects, and the proven research.
Thank you. Thank you so much for coming. And again, help me to thank Dr. Abbud-Madrid. Thank you.